Swayam Prabha. Digital India. Educated India.
Okay, so I want to circle back. So this is the last introductory chapter. So I will talk more details following this. So I just want to talk about this scale, this how you look at this problem at the big scale. And if you zoom in, there are lots of structures and mesoscale. And if you zoom in, you can look at individual particles. Okay. So in other words, one needs to look at this in the following. This is one way for people who are doing modeling and simulation. You might want to think about it. You know, one can talk about particle resolved simulation. So you talked about doing particle resolved simulation. Well, you can do 10,000 particles. Okay, you can study sort of like taking a computational microscope and look into a tiny little region of a fluidized bed, and you can study what happens. Okay, that's very good. But then you may develop drag laws and things like that, heat transfer relations, and then you can sort of broaden your viewpoint, and you take a bigger system consisting of million particles, etc. But now you cannot look at individual particles, what happens around them. You will have to use point particle approximation. You just simply say, well, I'm just going to move particle. Okay, you may use DEM. Some of you talked about DEM, where you say, oh, the particle is really finite only when it comes to collision, but otherwise you may ignore its finite size. But what it allows you is to study a bigger system, and you can look at these waves that I showed earlier, etc. You can study. In that problem, actually, we used Euler-Lagrange DEM method. Okay, we did take care of collisions, etc. But flow around each particle wasn't calculated precisely. So we just have to use some Pregard and then use some drag law and say, hope it's right. Okay. In fact, I don't know whether it's right, because those drag laws were developed for uniform flows, and clearly we were having bands, and still we were happily using the drag law. So it is only approximate. It's a mesoscale simulation that I showed. Okay. Now what happens is that when you have system which is much bigger, there are waves inside your cell, and you are talking about Euler simulation, two fluid model, and you're talking about drag. Now drag is varying within your volume. You have to somehow represent that. Okay. Now, not that we do it like that, but you know, that's where the next decade. So one of the things I want to do also tell you where the future lies. Okay. The future lies, that's where the kind of stuff that we want to develop is that all practical problems reside here. Fluidized bed problem, lots and lots of, if you want to solve volcanic eruption or sediment going down a river, none of them you are going to be able to solve only with million particles. You have big systems, right? But the question is, how do we do, a lot of people have done microscale, a lot of people are doing mesoscale. How do we take the best out of all these things and be able to do macro scale modeling and simulation that is as good as mesoscale and microscale in there. So that is where the current technology sort of lies, is that how do you develop real good closures that bring in all the missing information. Now I tell you, that's exactly what physicists did. Okay, because when you use Navier-Stokes equation, we use viscosity. Do we ever think about it? No, we are happy with it, and it works. That's because physicists, statistical mechanicians, and average all the molecular activities, and they gave one final number as viscosity or as conductivity, and it works. The question is that could we do the same kind of averaging for multi-phase flow, and when we do coarse-grained simulations, can we have good models that capture all the things that are going on inside that averaging volume. So that's where one of the holy grail is, and lots of people are working on it. Okay. Now, another way of looking at this is this problem. Say, for example, I just want to give you some example. So here is a river bed. You're looking from the top, and sand grains are moving as the river is flowing. And one of the interesting phenomena that happens is that ripples form. Naturally, this is top view, but what you're seeing in these red regions are nothing but the bed elevation is a little higher, and then it just forms ripples. Eventually, it may even form dunes. So environmental engineers or coastal engineers are very interested in this. And here, the same problem, looking at it in 3 different ways that I talked about. At the top, grain level simulation, we do fully resolved simulation. Not Ullmann's group did. I mean, that's a hero simulation. They used 100,000 particles. They did a huge simulation, and you can see these are accurate simulations, okay, because they track every single particle. But it cannot explain what happens in a coast because it's just not possible. But you develop drag loss, etc., and then we apply it in the Euler-Lagrange simulation, where we track about, in this case, maybe not a billion, maybe I cheated there, maybe you could do, but we use hundreds of millions of particles, and we track it, DEM simulation, discrete element. But the drag loss, we try to use some knowledge that comes from here, and you can see beautifully ripples form over. But this is only 25 centimeters. It's nothing, okay? But then the question is that how do you coarse grain this and then go to 10 meters of Euler simulations? But 10 meters is definitely nothing either. You know, real coastal engineers are interested in kilometers of things. Okay, so this is the kind of problem I was talking about, is the multi-scale modeling. Okay, now not that we need to do all of them the same person, but how do we work together and sort of link hands and pass knowledge and then be able to solve much more faithfully. See, one of the curses that people do simulate even kilometers. I just throw in a little bit there and a little bit here and stir it up, and whatever comes out, that's good, beautiful, colorful pictures. And partly it's also true. I'm not saying it's bad, but we don't want to be satisfied with that. So a lot of things that in multi-phase flow, what we want to do is that how can we make those simulations, which is what you have to do, very large scale simulation, how to make them better than what we are doing as of now. So that, and in one of the things I might also give is that sharing of a lot of information, and somebody said machine learning, we're working a lot. How do you take this information from this scale and pass it on to here? How do you take this simulation and pass it on here? Because this simulation, this mesoscale Euler-Lagrange simulation, took months to run, vast amount of data. Do you really want to just average and give one closure model and to pass it on here? That's a crime. There's so much information there. So we're using machine learning to find what is the best reduction that will give you a better model, better class of models that when you put in here will have all the smaller scale information in it. Okay, so that in a way that will be one of the frontiers of research in multi-phase flow. Okay, this is another problem, and this problem permeates in a lot of.
Any other way other than machine learning to do this, going from one scale to other?
Great. Machine learning is not the only thing, but the only thing that's really doable now, in my opinion. The reason is, suppose, let's think about it. When we do macro scale simulation, so let's say you want subgrid stress. Now we just say Smogorinsky model, and it only depends on something like that. I don't know what models you guys use. So you make a hypothesis that the subgrid stress is dependent on strain in some ways. But in reality, it could depend on neighbors' strains, past time, or in multi-scale problem, it may depend on your neighbors' arrangements and so on and so forth. In other words, models have to be made richer. The model, if you want modeling stress, it may depend on 10, 20, 30 or 200 different quantities. Okay? When you expand the parametric space, simple curve fittings, etc., doesn't not good enough. Now, this lower scale simulation has a lot of information, but if you're finally averaging and you get one curve or one data, you're throwing a lot of variable information. So one of the things that we are trying to do is how can we take some lower scale information and not even say what the model form has to be, because many times we say, oh, let's use sort of eddy viscosity model. Once you say that you have assumed a certain form, and that form may not be correct anymore. So I believe that machine learning has a lot to offer, and we have found a lot of really good ways to use it, but with good knowledge of the physics of the problem. Okay, I was talking about this problem, very similar problem. So here we have what we had was we have experiments where you have an explosive surrounded by a bed of particles like this. So the explosive is in the interior, and when the explosive goes off, it just hurls the particles, and that's what earlier I showed us fingers coming out, you remember. So to do that, we wanted to first understand how does a shock go through a bed of particles. I mean, nobody knows really. Okay, so we said that we're going to study, but this isn't good enough because we made a lot of assumptions. It's particle resolved simulation, but it's teaching us something, but not everything. Then you do a Euler-Lagrange GM, try to understand how force chains travel, etc., how the fingers form. Then you get knowledge. I mean, these are just show and tell. We haven't connected these things because still is out there. But the sort of like we want to do these things, but it takes a lot of effort and time. So how do you get this knowledge and pass on to Euler-Lagrange Euler simulation, where you can talk about a big explosive system with trillions of particles, and how do you do that? So again, this is another example of that. Okay, so it's this sort of summary is that it's impossible to solve the problems as a whole. So we need to divide and conquer. One good thing about phase flow is that there is natural breakpoints in length scales. Okay, in classical turbulence, the same problem exists, but I see less hope there. Here's a lot more hope I have in multi-phase turbulence. So anyway, one needs to focus on downscaling as well as upscaling. That lecture ends. I want to now get into some details of modeling, starting from a single particle, etc. Okay.
So when we're talking about the macro scale simulation, so I work in the solid rocket motor problem. So then how do we comment upon the accuracy? Like what comments can we even make in that respect?
Well, compare with the experiments.
If we do that, so then like for my particular problem, I don't have enough experimental data to validate it against.
Make some pretty pictures and people who are giving you money will be happy. But at the same time work on the science. Okay, I mean it's a difficult problem. Everyone is dealing with difficult problems. Okay, but you know that's an interesting point. A lot of things that I'm talking about is very fundamental. Okay, now you want to look for opportunities where you want to address while solving real problems of the day. Okay, so many of us, you can't wait for another 20 years to solve some of the problems. So you got to go do it. But I think there is always a fraction of our time we can devote to finding where the weak links are and fixing them. Okay. If we are aware, at least we will be cautious, and that's why nobody builds a next stage rocket without actual experimentation. They don't trust computations yet. Okay, but we want to get there with modeling and simulation maybe someday. And machine learning, I really think that there's a lot to give us, because some of us are doing micro scale simulations, like he talked about particle resolve simulation. Lots of people are doing Euler-Lagrange GEM. Other people are doing Euler-Euler. It's just that we haven't hooked those things together yet. It's especially the way computer scientists have done. You look at machine learning, these TensorFlow networks, etc. They work really together, and everybody's contribution adds to some big part. But we mechanical engineers, we really are sort of siloed. I do my simulation, I publish my papers, but never share anything. Okay. The question is, how do we do a lot of our simulation and spread the knowledge around and really link the scales? That's the next best revolution. I don't know how to solve it, but as the editor of multi-phase flow, those are the kind of stuff that we want to do. We want to encourage young people to find ways so that we can leverage a lot more out of what we do than what we are doing today. Okay, we're not really breaking. Well, we are making progress, but not revolutionary progress. So especially with machine learning, I'm really hopeful that we can come to a stage where we can really make substantial progress in our understanding and modeling of multi-phase flows. Yes.
Just maybe before we start something new, maybe we just summarize.
Yeah.
So you have talking about micro scale, meso scale, and macro. So can you just tell them, what exactly is involved in these micro scale models? I mean, what are the kind of equations? And what do you do in the meso scale? How do you go from one to the other theoretically? I mean, and that kind of a thing. So that may give them a good picture, because like you said, everybody is doing whatever he's doing. They don't know the connection between the other two scales. That might be a good way to end today.
Thank you. So at the micro scale, perhaps it's the easiest, because you are trying to solve governing equations, no averaging. When you solve particles. Now, of course, some of you talked about micelles and things like that. So there are subscale physics. That's why, when the picture that I did, there was an atomic scale going to micro scale, etc. So we tried to, at the micro scale, by limiting our vision to only few particles, few systems, we try put all our energy in making our simulation as close to first principles as possible. Okay. The challenge there is this micro scale picture, few hundred particles, is happening in a big environment. Your micro scale must be reflective of what's happening. So typically you may have to study many different volume fraction, many different particle sizes, that's very hard. Okay, many different Reynolds numbers, etc. So doing a micro scale simulation is not a problem. By doing micro scale simulation for every scenario that you are likely to see is the challenge. Okay, so there I will tell you one thing. We are now trying to do something. You have all seen machine learning trying to learn and draw a Van Gogh picture or things like that, just generative models. So one of the very interesting thought that we have is, well, if I tell machine learning how the answers we got for, say, a distribution of 100 particles at, say, 10 different Reynolds number, 5 different volume fractions, some scenarios, and teach it and say, you go produce CFD results for million other scenarios, and it does to 95% accuracy. So in other words, you can use machine learning to fill in the gaps. So in other words, as Professor Pushpavanam pointed out, micro scale, is easy to solve in some ways, because you're solving Navier-Stokes equation and moving particles, etc. Of course, we talked about some other complexity that can happen. But then doing many such data, maybe millions of microscale simulations you have to do. So you say this is how it looks like, this is how it looks like for varying parameters. Then if you have a complete knowledge, then you say, I know everything, every possible scenario I know. Now let me develop a model with that. At the mesoscale, we have sort of coarse-grained, we've gone a little bit bigger. We have, say, millions or billions of particles, where we are tracking the particles, not resolving the flow around them. But we have to use models for drag, etc. But now we have a library of information on what happens at the microscale. If you can condense it, and I have some results, I will try to show it on Thursday or Friday for you guys. We can now do Euler-Lagrange DEM simulations. You may use million grid, but what if it can capture all the physics as if you have done a particle resolved simulation? So your model is so good that even though you are not solving the flow around the particles, it captures the right physics. Okay, so it's like you had done a trillion grid simulation. You are not going to do it, but it has that much physics. So in other words, now you are now doing a mesoscale simulation that has all the essential ingredients in that. So what I mean by mesoscale simulation is Euler-Lagrange simulation with point particles, moving them using drag laws, maybe DEM, etc. Okay. Now the same problem going from mesoscale to macroscale, you have to now do the mesoscale for every different scenarios that's likely to be seen in a macro scale, which means you have to do maybe tens of thousands or millions of mesoscale simulations. But now these mesoscale simulations are as good as possible. Okay? But here again you can use machine learning to do generative models and then develop better models that can be upgraded to, can be used in macro scale simulation. In macro scale simulation, which is trying to do a full riser in a chemical industry or full solid rocket motor simulation from the head end, star grain to the body and to the exhaust plume, that's a tough simulation. But now you have a whole system. You have to do Euler method of some sort. You have using subgrid models of varying kind. But now these subgrid models are very complicated, but they are very well informed because they have been trained from deeper physics embedded in them, so that you could trust those results. So that's the kind of vision that we have. So I would say, to summarize, microscale is fully resolved, particle resolved kind of simulation. Mesoscale is sort of maybe Euler-Lagrange simulations, DEM, and macro scale will be Euler-Euler simulations of some sort.
And at each level, you have to start from some kind of first principles model, some assumption. You can't go from one to the other by averaging or anything.
Well, but once you go to mesoscale and macro scale, averaging is unavoidable. See, so one of the ways that you have, in the case of solid rocket motor, maybe 10 meters, and there are aluminum droplets, oxide particles of 1 micron and so on. So you have length scales sub-micron to 10 meters. There is no way we can handle that. And that's what I said, that the entire whole range of scales is not possible. So maybe your grid may be maybe a centimeter. So everything that happens at the macro scale. So what happens within that grid has to be modeled in some ways. Okay, and that's what I was talking about. Yeah. Any questions?
So one more question I
Yeah.
had. So whatever methodology and whatever you are saying for these multi-phase flows, shouldn't the same things be applicable on understanding single phase turbulence as well?
Yeah, yeah, absolutely. And people are doing, you see, one of the nice thing about multi-phase flow, in my opinion, I said that few times, is that you know where the particles are. So particles serve as a marker, and particles are clustering. You know where it's sort of. Now in turbulence, there is a wide range of eddies and scales, etc. It's low dimensional. There may be a low dimensional projection, but how to project it is very hard. Eddies form and die. Thankfully, particles don't form and die by their own. Okay, so those markers can be tracked and kept track of. That's why I said that multi-phase turbulence in some ways is complicated, but in terms of divide and conquer, it's a little more hope than straight up, say, atmospheric turbulence. Okay, one of the challenges that eddies come, go, and they are very important. How do you divide and conquer is not very straightforward. So one of the hope I was having is that maybe multi-phase flow turbulent closure approach can teach us how to do vortex-based closures for classical turbulence.